Okay, morning everyone. Let's get started. So welcome back to your second week. Probably, well, third week I suppose if you were here in week 0. Okay, so last week we left it that we'd almost finished deriving the thin lens formula. But because it was almost a week ago now, let's sort of just do a quick recap of where we were and where we've got to. So I think this was the slide I'd left it at, but let's just go back a few more slides just to remind us. So we'd actually started off by looking at prisms, actually. I won't start from that slide. Okay, started off by looking at prisms, and we had derived the fact that under the small angle approximation, then, the deviation angle is given by n-1 times a, where a was the apex angle of the prism, n was the refractive index of the glass, so we're assuming glass in air. Okay, and so under the small angle approximation, this deviation angle was independent of the exact ray. And then we sort of moved on to looking at prisms as a way to model a lens. So we sort of looked at this and argued that these three rays shown here would all come to focus at a particular point. Then argued that actually looking at a lens, the same three rays would also come to focus at a particular point, because we argued that as far as the light ray is concerned, it's just seeing a locally flat surface, so to it might as well be hitting a prism, where the prism apex angle is defined by the angle between the tangents to the curves at the point that the light is hitting. And then we went on to say, well, okay, can we figure out the exact shape of this curved surface so that not only these three rays will be brought to a focus, but every ray would be brought to a focus at the same place, because that is what we need for a lens to function as a lens. Okay, a few approximations, right, and then we got to here. So let me just recap where we'd got to. So what's being shown on this picture is a light source spewing out light rays. We'd chosen one of them, one that happens to hit the lens at a height h above the axis, labelled on a couple of angles, and so the deviation angle here is given by this theta plus phi. Hopefully you will have this written down already, so I'm just recapping because I'm going to carry on from here, so I need it written down anyway. So it's given by theta plus phi, also given by that. And then in the small angle approximation, we can also therefore write that means this is true. Okay, so just quickly. I don't know if anyone's up there. It would be good if that was switched on as well, wouldn't it? But I'm not quite sure how to do it. Don't know if there's anyone at the back. Sorry, Gina? It broke earlier. Okay, thank you. Right. Hopefully you're all right with that one. Right, and then we'd left it that I argued that this thing will function as a lens, provided that we can write the apex angle as h over c, where c is some constant, which we're about to determine. Because what you can see is that in that case, then what we will get from this is that all of the h's will cancel out, and we will get that equation, which hopefully is already looking familiar to some of you as the lens equation. But what this is going to say is that because all dependence on the height h, or equivalently the angle theta, has disappeared, then this means that any ray is going to be focused at the same point. So if we've got a point source here, spewing out light rays, a distance u from the lens, then all of those rays, regardless of which they are, will all be brought to cross the axis here at a distance v away. So this is the requirement that we need. So we need the apex angle to be linearly proportional to the height at which the ray strikes. Okay, so there's the optic axis. This is supposed to be the horizontal axis there. So we need something looking like this, right? At a height of a height of 0, we need that would imply that an apex angle is 0, right? That makes sense. And then gradually this thing sort of goes up linearly in some way, in some sort of curve, right? That's what we're going to need. Okay, Right, so that's where we were up to last week. Hopefully you've got everything written down and you vaguely recall that. So now we're going to actually work out what that constant is and work out the shape that we need. In fact, I'm not quite going to do that. I'm going to tell you the answer to the shape we need, which is circular, and then show that that is going to satisfy our condition that A is linearly proportional to H. So I say circular, I mean spherical, but of course I'm just always writing or drawing a 2D cross-section. So it looks circular on the paper, but it's a so-called spherical lens. Okay, so this diagram I'm going to try and explain reasonably carefully. Right, so I've already drawn, so this is our lens or half of our lens, and I'm drawing these already as arcs of circles. I'm assuming the answer. I'm going to show that that is the right answer by the fact that it's going to satisfy this condition. So what these R1 and R2s are the so-called radii of curvature of the lens. That is, if I were to stick my compass here, right, and draw an arc of a circle of radius R2, I would get that curve, right? So that's all that is. So there is nothing on this diagram, which is the thing I really want to drum in because it can cause a bit of confusion. There's nothing on this diagram that is to do with the light source at the moment. This is all due to the geometry of the lens itself. Okay, so I'm just drawing two arcs of circles with radii R1 and R2. I've made these particular radii of curvature the ones that sort of cross the middle of the lens at the height h. That's the radii of curvature I'm interested in because I want to get what I'm going to want to do now is get an expression for the apex angle in terms of R1 and R2, but I want the relevant apex angle corresponding to, to the height at which my ray is actually striking. Okay, so that's why I've drawn them like that. Labelled on some angles, alpha and beta. I think everything you need is actually written on the slide. I've not left a blank box, but still I think it could do with a bit of supplementary information to make things clearer. So I'm going to try and reproduce that diagram roughly. Okay, so we've got half of our lens here. Okay, I've got one radius of curvature there, another there. So that was R2, that was R1. I've got alpha, beta. Probably should have drawn this bigger. Right, now, okay, now remember, even though it doesn't look like it, we are in the thin lens approximation, okay? So actually these sides coincide with the middle, okay? So the relevant, so here I'm drawing the tangents. So that's the height h there. Now, right, so if we try and, so this would be, this here, you may want to draw this on your slide, would be the apex angle corresponding to the relevant prism that my light ray is going to hit, because my light ray is going to hit at a height h, right? Now, hopefully you can see that this, if I'd drawn it well, is a quadrilateral, okay? These are the tangents to the sides of the lens, so that's a right angle. That's A, and therefore that angle is 180 minus A, and therefore so is that angle. Okay, hopefully you can label it on better than my diagram. Oh, on there. Okay, so what that means is that with that geometry, the apex angle A can be written as alpha plus beta. Okay. Given that's not a great diagram, and I just double check that you're clear with that, you might want to look at that. You're happy with that? Okay. And not only that, but because we're always working in the small angle approximation, we can therefore write this apex angle in terms of the radii of curvature, right? So roughly h over R1 plus h over R2, because sines are equal to tans are equal to thetas. Okay. So now we're going to go back to the original diagram on slide 54 and just put everything together, right, that we now know. So this is to be written in the box. That was just some supplementary information for the previous slide if you wanted it. Okay. So we have, now we now are back to the diagram that is showing the light source. Okay, so same diagram as was on slide 52, but it's just that now we know the relationship for A that we're going to stick in. Is it still showing at the very top? Yes, it is. Okay. So what you can see is that I do have here the form that I wanted, right? So a circle or a spherical lens is the right answer. We've got something that is proportional to the height h at which it hits over some constant or multiplied by some constant. So we've got, this isn't actually to go in the box, but I'm just, right, that's what we've got. Okay, right, so what we're going to put it all together in the box. So now we know from before that we have this, but we have a relationship for A now, and also we can do the usual small angle replacements for theta and phi. And I'm going to say that that is alpha plus beta, which is, as we've seen, n minus 1 h into 1 over r1 plus 1 over r2. All the h's are going to cancel, and so we have our final lens formula, which looks like this. Sorry, I'm in front of it, aren't I? And I'm going to write that as well as 1 over f, for reasons which we'll talk about in a minute. But you will, of course, have seen this if you've done anything on the lens formula at all. This f is going to be called the focal length, but I'll explain in a minute why it's called that. So this is it. This is the thin lens, or lens maker's formula. Most important formula in all of practical geometric optics. So one that you will need to remember. Okay? Right, so what it's telling us is that if I have this point source of light on the axis, a distance u away, then all of those rays will be focused down across, at a point on the axis, a distance v away, and the relationship between u and v well, it's related like this, and it's dependent only on properties of the lens. It doesn't depend on the light source itself. Okay? Everybody happy with that? Okay, don't see any complaints, so let's just say a few words about this formula in the context of Fermat now. So just thinking about how this must work if we think of it in terms of Fermat's principle of least time. So Fermat said that the light must take the path which takes the least amount of time. So we know, though, for a lens to work properly, all of these rays need to focus at the same point. And so what that must mean is that all of these paths that I have drawn here, and any other paths that I cared to draw through the lens, they must all take they must all be a minimum time path, right, for this to work. Well, how can they all be a minimum time path? Well, only if they all take the same amount of time. Okay, so Fermat, from Fermat's perspective, he said the lens must be shaped so that the longer time in air travelled by this upper one is exactly compensated by a shorter time in glass. Right? And as long as everything compensates exactly so that all of these paths would take the same time, then the lens will function as a lens. So I'm not going to say more about that because there's a problem on the problem sheet which asks you to think about this a little bit more in the context of Fermat's principle. So I'll leave that as an exercise for you. Okay, so let's turn back to the lens formula. So here it is again. As I said, the most important formula in all of practical geometric optics. And let's just look at a couple of special cases. So first of all, let's just look at the case where we have an object from far away, sort of spewing out light rays from a distant object. So they're coming in, so this is the lens, and these light rays are coming in parallel to my lens. So what we're saying is that u tends to infinity. Well, that must mean that 1 over u tends to 0. And if we look at our lens formula, then that means, no, I don't want to get in the way of my diagram, sorry, that means that 1 over v equals 1 over f, and therefore v equals f. So what's going to happen with these parallel rays coming from infinity is that they are going to focus down at a distance v equals f. That is, in fact, why this is called the focal length. It's based just on this property, that if you have parallel rays coming from a distant object, then all of those rays will be focused at the focal point, one focal length away from the lens. Okay, so another special case is sort of the other way round. Let's say I've got light rays coming from a point source here, which I'm going to place one focal length away from the lens. Okay, so what does that say? Well, that means that 1 over u equals 1 over f, which must mean 1 over v equals 0, which must mean v tends to infinity. So these are going to come out of the lens parallel, right? We could have known that just from the reversibility of light rays, right? That's kind of obvious behaviour that was going to happen. Okay, but these sorts of properties are going to be important for where we're going, which is why I'm sort of being a bit explicit there. Okay, so just as a bit of an aside, I'm just going to say a couple of words about the so-called Newtonian form of the lens equation. So what we have written up here, so let me write it again, in fact. So 1 over u plus 1 over v equals 1 over f is called the Gaussian form of the lens equation. Okay, and that is just just the form that is most commonly used now, and it's where. So this is the lens again. It's where the object and image distances are measured with respect to the lens. So let's say I have an object here, that's u, and then let's say it forms an image over here, that's v, and obviously this is the focal length. I've labelled it f1, labelled the two focal points as f1 and f2 because one is called the primary, one is called the secondary. That's going to be important for a little hint I'm going to give you in a minute. Okay, so that's the Gaussian form of the lens equation, but then Newton decided that instead he was going to measure distances of objects and images from the nearest relevant focal point instead, right? So he measured objects and images like this, so that we had the relationship u equals f plus x0 and v equals f plus xi. Now, if you do that, and you pop these, you substitute this u and v into the Gaussian form, and you rearrange for 2 or 3 lines, what you get out is this so-called Newtonian form of the lens equation. So it looks quite nice and simple. Dropping my chalk today. Right. So what you get is x naught xi equals f squared, and that's the Newtonian form. And it looks quite nice and simple, and it can be nice and simple to use in some cases. The main reason I'm drawing it to your attention is not because I ever expect you to really particularly use it, but just because you may come across it in books, and so I wanted you to know what it is. The other reason is that there is a problem on the problem sheet which just asks you to do this derivation, which isn't too difficult. I'm sure you'll be fine with that. But then it asks you to go on and just think a little bit more about the form of this equation and just sort of justify why it gives you the right answers for different kinds of lenses and for different kinds of images. And for that, I think really you need to know a particular set of conventions, and I'm going to give you those conventions now just to help you with that problem. I'm in 2 minds as to whether this little bit is worth it, but it'll only take us 5 minutes. I think I've done it for about 3 years, giving these hints. Before that, I didn't give the hints. And I'm not sure I've seen any difference in the quality of how the question is done, but never mind, I keep trying. So I'm trying to help you here. Okay, so it will look like just a load of facts at the moment, but when you come to do the problem sheet, you know, look back at whatever you're going to write now and hopefully it will help. So I'm going to give you just some sets of sign conventions and definitions for how you measure x0 and x1, and xi, sorry, which will help you figure out what the question is asking. Okay, so x0, define this as the object distance from the primary F1 focal point, which is why I labelled F1 and F2 there. Furthermore, it is going to be positive if left of F1. Okay. Xi is going to be the image distance from secondary F2 focal point, and it is going to be positive if right of F2. So in the diagram that I drew up there, everything is positive so far, so it's all nice and easy for converging lenses and so-called real images, which we'll talk about soon. Okay, and then finally, I'm just going to give you a few facts for converging lenses versus diverging lenses. So if I have a converging lens, converging, and my light is coming from that direction. Okay, then that is F1, that is F2, and F, the focal length, is positive. Okay, and then for diverging, things switch round. Light's still coming from that way, but that is now the secondary, that is now the primary, and F, as you probably know, is negative for diverging lens. Right, now those facts on those two boards should give you everything you need to do the question, the problem sheet thoroughly, and sort of figure out why this Newtonian, the question's just all about looking at this form of the Newtonian equation and just verifying to yourself that it gives the right answers for real and virtual images, which we've yet to talk about in detail, converging, diverging lenses, and so on. Okay, so that was a little bit of an aside. Right. Pause for a second, because we're about to go into, well, same topic, but it's still on lenses, but talking about extended objects. So just check that everyone's happy to now. Yes?
Sorry, if the focal length distance are not equal, does the Newtonian form can it be simplified such that...
The focal lengths are always equal to each other.
For thick lenses it's not.
Sorry?
For thick lenses it's not.
For thick lenses. Does the
Is there a simplification for thick lens that the Newtonian form is x not x1 equal to x1 x2 or something like that?
So this, everything we've done is in the thin lens approximation, everything we've done, right? Yeah. So indeed you would have to modify both the Gaussian form and the Newtonian form if you want to talk about thick lenses, and we'd have to go through from the start, right, and derive everything again properly, which would take a long time. Right, so...
the for thick lens, the equation isn't just... you cannot just change f squared to f1.
Because I can't quite hear you, so F1 to F2 plus... F2. I think there's a bit more complexity to that, but yeah, but I'd have to check. Because bearing in mind we have to take into account also the object distance and the image distance and stuff, including the thickness of the lens and everything. So you'd have to change everything slightly. Okay. So now we're going to move on to talking about extended objects. So everything we've actually done, just flick back quickly to this sort of diagram. Everything we've done so far is strictly for point light sources, okay? And so that's what we've done. We've derived the lens formula to show that all this works for point sources. But what about extended objects? So we're going to look now, we're going to use the method of ray tracing, so-called method of ray tracing, to figure out the sizes and the locations of images for not just point sources, but now extended objects. So this is going to be our extended object here, this sort of green arrow or skinny pine tree, however you want to view it. And you can look at this thing or treat it as if it's point sources of light all the way up, okay? So any point on it can be just treated as a point source of light spewing out its own set of light rays. So we already know what the point source on axis is going to do because we just worked it out, right? It's going to sit over here, it's going to obey the lens equation, it's going to have an image also on the axis. In order to figure out what this image is going to look like, we only really therefore need to figure out what's going to happen to the point source of light that's forming the very top of the arrow, right? If we can we know what's happening to the bottom, if we can figure out what's happening to the top, we can just sort of draw in the rest of the image. If you wanted to, you could draw, of course, a much messier ray diagram, but there's just no point. Okay, so what we're going to do is use what we know so far about the way lenses behave to be able to construct these so-called ray diagrams to figure out where the image actually sits. Now, I'm only going to, at least in the main set of lectures, I'm only going to show you that 3 particular rays are going to come together at a focus at a place that also obeys the lens equation, i.e. the situation is going to look like what I've drawn here, but we're going to show that more properly in a minute. I'm only going to show it for 3 special rays, 3 rays that are the properties of which are very easy to understand. Of course, if you wanted, you could go away and prove to yourself that any ray you chose at all, any arbitrary ray, would also come to focus at this point. That must be true if this is functioning as a lens. If I have time at the very end of the lectures, I'll do that proof for you. It's quite fun, it's not too difficult, but it's not something that's on syllabus, and these 3 rays are the easy ones to look at. Okay, so, right, so method of ray tracing. So what do we know so far? Right, well, it's off the board now, but some of what I wrote on the board earlier is going to be useful for this. So let's take the first easy to understand ray. So that's going to be the one that just goes straight through the middle of the lens, okay? And we know, because we have derived within the small angle approximation, we have derived that formula. So we know that if we're going through the middle of the lens, the apex angle is 0, and therefore the deviation angle is 0, right? And so that ray is just going to go straight through the lens and be undeviated. Now, of course, looking at this picture, again, I'm drawing these lenses a little bit fat, okay? But always remember that we're working in both the paraxial approximation, small angles, and rays close to the axis, and also in the thin lens approximation. So while you'd be forgiven for thinking, well, that ray doesn't really look like it's actually going just through the middle, it's actually hitting the lens a little bit above. Remember, we are in the thin lens approximation, so these edges coincide with the middle, and actually also we're in the paraxial approximation, so also it's hitting the lens negligibly, a negligible distance above the axis. And so that ray really is hitting the center of the lens right at the A equals 0 point, so it just goes straight through, nothing happens. Okay, so the other easy to understand ray is the one that comes down. Oh no, let's do this one first. It goes parallel to the axis, okay, and from what we saw earlier, we know that will be deviated through the focal point. I can carry on drawing it if I want, and these 2 rays are going to meet somewhere here. And then the third easy to draw ray is the one that comes down through the focal point. As far as the lens is concerned, that looks like it's coming from an object sat at the focal point, so that's the one that will come out parallel, and as long as I've drawn it correctly, those 3 rays are going to meet, and indeed every other ray would also meet at that same point. But all you're ever going to need to figure out where images sit are these 3 rays. Sometimes only 2 of the 3 rays, you know, if you could, sometimes you could only draw 2 of the 3 of them, so sometimes you have to do it with 2, but it's always good to draw the third as a sort of verification if you can. Okay, so that's what's going on, but let's just sort of prove to ourselves with a bit of geometry that I haven't just sort of fiddled the drawing and that it really is, that these rays really are all meeting in the same place. So the first thing, I'm just going to use similar triangles for this, okay? So I've drawn on the similar triangles that we're looking at right now. And the first thing to notice is simply that h over u equals h over v. Okay, and so what we're saying is that h is the height of the image is equal to the height of the object scaled by v over u. Okay, I'm going to leave that on the next slide. Okay, so on the next slide we're going to look at some different similar triangles. We're now bringing in the top ray and also the bottom ray. And what we can see from this is that h over f is given by h plus h over v. And we know from that 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 is simply h over u, little h over u plus little h over v. So all our little h's cancel. And we've recovered the lens equation. Okay, so what we're saying by this is that not only points on axis satisfy the lens equation, but also points off axis satisfy the lens equation. And so our image really is going to look like this. Any point source, a distance u away from the lens, whether on or off axis, will all come to focus at a point, a distance v from the lens, and you have to do this ray tracing to actually figure out exactly where the point will sit, where it sits away from the axis. Okay, if I wanted, I could have drawn some different similar triangles and come up with the same result. That's just there for your reference. Okay, and again, for your reference, I'm just giving you here the rules of ray tracing. So you'll see this in books. You will probably, many of you will already have done this at A-level a lot. So you'll know about it. I'm not going to read this out loud now. It's there for convenience for you. The first 3 are to do with the rays that we have just talked about. There's the one that goes through the middle, passes through undeviated. There's the one that is parallel to the axis, passes through the focal point. And then there's the one that passes through the focal point and comes out parallel. The only thing I'm going to talk about in a bit more detail just now is this 4th one, which is not usually quoted as a rule of ray tracing, but is useful for you to know. So that is to do with what happens if you have rays. So here's a lens. Now, if you have parallel rays, we know what happens, right? They get focused on axis at the focal point. But what if you have rays that are parallel to each other, but not parallel to the axis, okay, like this? This can be useful to know. Well, it's reasonably simple to understand what that is going to look like as well, because you can always choose one of these rays to be passing through the focal point, right? You can always choose. So you've got one ray that's clearly just going to pass through undeviated if it goes through the center. You can always then choose another ray parallel to that that passes through the focal point, which you know will then come out parallel, okay? And so if you do a little bit of geometry, don't think I've drawn it too well, but you'll see that that is a distance f, as that was a distance f, right? You've just got a parallelogram here. And so what happens is that those rays are focused at a point, a distance f away, but off axis, right? So they will be focused somewhere in the so-called focal plane, which is there, a distance f away. Okay, so a little bit more about the focal plane. There we are. So just to illustrate with slightly better diagrams what I've just said. So here's some rays coming in parallel to the axis, being focused on axis, a distance f away. It's more rays coming in from the top, being focused somewhere on the focal plane below the axis, and likewise for rays, or similarly for rays coming from below. And here's the whole thing together. So what's going on is that you're just getting these sets of parallel rays that are coming in at different angles. They're being converted to different positions on the focal plane. And this is exactly the basis of a camera, right? That's exactly what's going on in a camera. You've got it's a rather simple piece of equipment, really. You've essentially got a lens, a movable lens, and you can put, some photographic film or a CCD chip or whatever here to actually detect your picture. I've assumed here that the object you're looking at, or you're pointing your camera at, is very, very far away, very distant. But of course, it might not be the case, but that's why you can focus your camera, right? If the object is a little bit closer, you'll have to adjust the position of the lens so that your distance V is larger, or sometimes you can adjust the focal length instead. But that's the basis of a camera. Okay, everyone happy up to now? So I now want to talk a little bit more about real images, the concept of real images and virtual images. So I've mentioned them quite a few times, and also we've said that we're using the real is positive sign convention as well. And I think I probably mentioned that what that means is that real objects and real images are going to have positive distances. So now we're just going to talk in more detail about what I actually mean by real images and virtual images, and I'll also hopefully have time to get on to telling you a little bit more about the sign conventions that I've been talking about. So far we've just been using it, but I'm going to say a few more words about it. So what we've said up to now is that if I have a converging lens, okay, so this is a converging lens, I'll just call it C lens, hopefully that's enough for you, right, and I have some sort of object spewing out some light rays, okay. Now as long as that object is placed further away from the lens than the focal length, then those rays will converge down like this to some point, a distance V away. Now, so that's what we've been looking at, the situation we've been looking at so far. Now, if that is the case, then these light rays really are converging back down to a point. These light rays are meeting again, okay? If that happens, that's what we call a real image, okay? And if I were to stick a piece of, a detector here, again, photographic film or a CCD chip, or just put some paper there, right? I would be able to actually see that image. I'd be able to project that image onto my detector, and my detector could be as simple as a piece of paper. And that happens because the light rays really are converging. I can also, if I want to, detect these images indirectly. I could just put my eye here. And to me, it would look like these light rays were apparently diverging from a point over here. So I would see that image. So real images, light rays are really converging to a point. They can be detected either directly or indirectly. So what are the properties of real images? Well, so here's the ray tracing diagram again for an extended object. One thing you notice is that a real image is always going to be inverted. If you do the ray tracing properly, you'll see that that is always going to happen. And in general, also, it's magnified. So this is called a linear magnification factor, this V over U. Now, by magnified, I just mean it can change size. V over U may be less than 1. It may be greater than 1. We'll see the conditions in a few minutes, as to when it's going to be enlarged and when it's going to be reduced. So magnified, I just mean scaled in size in some way, okay? And we saw that, I think it's still up there in the box, right? We saw how to derive that just using these similar triangles shown here. Just a quick mention, this also brings in yet another sign convention you may see. So either in different books, you'll see magnification either defined simply as V over U, and you're just supposed to know that it's inverted for real images. Or sometimes it's defined as that minus V over U, so the minus sign is kind of inbuilt in there, and that minus sign is telling you that it's inverted. So you may see both or either, and you just have to sort of know what's going on. Okay, so just a special case as well is when this is useful in practical terms, and we'll see a practical use of this later, probably in the sixth lecture, so-called inverting lens. If you put your object precisely at a distance 2f away from the lens, and you solve the equation, so what we've got here is u equals 2f, and I'm going to solve for v. So I've got 1 over f minus 1 over 2f, that equals 1 over 2f, and so v equals 2f. So in that case, you've got a situation where your image is exactly the same distance away from the lens as your object, on the other side, of course, but just inverted. So you've not scaled anything. Your scaling factor is just, where is it? It's just 1. So you've got exactly the same image size as object size, but you've just inverted it, and that, as I say, can be useful in some practical applications, which we'll talk about later. So it's so-called inverting lens. Actually, also, this distance of 4f in between the image and the object turns out to be the minimum distance you can ever get between an object and an image. And again, I'll leave that because it's an exercise in the problem sheet for you to prove that to yourself. It's not immediately obvious from this, but it's, you know, relatively simple to prove. Okay, what about virtual images? So we've seen a converging lens will form a real image if the object is placed outside the focal point. If you place an object inside the focal point, then you get what's called a virtual image. So what's going on there? So again, this is going to be a converging lens. If I make u be less than f, okay, so here's my point source of light, it's spewing out light rays, the lens will do some converging towards the axis, but not enough. It's not strong enough to bring the light rays back down to the axis. So these light rays are diverging on the right, they're never going to meet again. But if you, or on the right-hand side, but if you just trace those rays back, okay, it will appear, if you were to put your eye there and look at it, it would appear to you that light rays are diverging from some point behind the object, right? So you can see that, and that's called a so-called virtual image. Virtual because light rays never actually ever met here, not really, just appears to you like they did. You can't detect these directly. If I were to stick a piece of paper there or some photographic film, nothing would happen because no light rays are really meeting there. But to you, your eye and brain system, you can look at this and it looks real. It looks like a real image. Okay, so these can only be detected in an indirect way. Diverging lenses, as we'll see in a minute, also always produce virtual images. So virtual images, very familiar to us. We've seen this picture before back in the first lecture, but the image in a mirror, right? That's a virtual image working in exactly the same way. Okay, so what about extended objects? If I wanted to draw the ray diagram for an extended object for a virtual image, this is what it would look like. So here's my object here, placed closer to the lens than the focal point. Let's just run through the special rays. Here's the easy one. This is always easy. It passes through the middle of the lens. This one then is the one that's coming in parallel, passing through the focal point on the other side. Of course, these rays are diverging, as we've just discussed. On the right-hand side, they will never meet to form a real image, but I can trace them back, and you can see that they're meeting. Let's just do a sanity check with the first special ray. The third special ray. This is the third one. It's the ray that looks, as far as the lens is concerned, it looks like it's coming from this focal point, right? It's not actually, but if I were to extend it, it would go through the focal point. So that one is the one that comes out parallel, and again, if I extend that back, it meets at a particular point. So you get this virtual image behind the object. It is always upright, and it is always enlarged. What about virtual images with a diverging lens? Okay, so I'm just drawing it here for a point source of light. So here's my object. Here are the light rays being spewed out. A diverging lens will, of course, do exactly that. It will cause the rays to diverge away from the axis. Never, never, never can you get these to actually meet on the other side. But again, you can trace these rays back and see this virtual image on the same side of the lens as the object. In this case, if it was an extended object, Again, the virtual images are upright, but now they're always scaled down, still by this V over U. And I'm going to leave that as an exercise for you to draw the ray diagram for the extended object. I've not included that in these notes, just for you to get a practice of drawing ray diagrams. Okay, so here's what we know about lenses. Right, so broadly, this is a summary just for your reference rather than, you can find this easily in a book, but I've just copied it here for your convenience. So broadly, there are two types of lenses, diverging and converging. Diverging lenses are actually very simple in some sense. They do one thing, and that is they produce virtual images. They're always upright, and they're always smaller than the object, so they're always reduced in size. Converging lenses are more complicated because what they do, or what kind of image they produce, depends on exactly where you put the object. So we can have a real image if we put our object further away than the focal length. If we put our object at the focal length, we get a parallel beam of light out. Again, practice drawing the ray diagram because we'll come back to that particular situation when we talk about magnifying glasses. And then if you put the object within the focal length, you get a virtual image. And whether, if you are getting a real image, whether your object is reduced in size, same size, or magnified, depends on exactly where you put it according to the information I've put here. Okay. So, I think just before we finish, I'm just going to talk a little bit, if I've got time, about sign conventions a little bit more, as if I've not mentioned them enough, but we're actually going to talk more about what I actually really mean now. So that hopefully, the words make sense when I'm saying real is positive or geometric. Okay, so we've got our lens formula. 1 over f equals n minus 1 over r1 plus 1 over r2. Now, I have said a few times that we have been working in the so-called real is positive sign convention. So now we sort of know a little bit about real and virtual images. I can say a few more words about this. So what I mean in this real is positive sign convention is that all real objects and real images are going to have a positive distance. So a real object would have a positive distance u, a real image would have a positive distance v, and a virtual object or image will have negative distances. The other thing about the real is positive is that there is a convention for the radii of curvature as well. Right, and I added in a couple of words last night, and it's these words. You won't have that in your notes. Could you please add that in, and I'll explain why that's important in a minute. So just that in air in brackets. So what the sign convention for the radii of curvature means is that right, hang on, let me just draw it on first. So that's one was R1, one was R2, wasn't it? I can't remember which way I did it. Probably that way. Right. Now, in the real is positive sign convention, the radii of curvature are positive if they cause positive deviations towards the axis, if they cause a deviation towards the axis, sorry. So a convex lens like this, for example, sitting in air, both surfaces would cause a deviation towards the axis. So both R1 and R2 are positive in this definition, right? Now, if I forget to say why I've added in the words in air, because I want to say a few other things first, then shout at me because it is important. No, actually, I can do it now. Let me do it now. I'll say that now so then I won't forget it. Right. Now, the reason, so the sign of this R1 and R2 is defined only by the behaviour of the lens if it were in air. So in this case, I've got this shaped lens. Both R1 and R2 would be positive in this case. Now, the reason you define it only by the behaviour in air is because I could have a situation where I have exactly the same lens, but let me immerse it in some very dense oil or something like that, right? And I'll call that N1 and that N2. N2 can still be glass, or we could be talking about an air bubble in water or something, right? I'm just talking about a situation where this refractive index is actually now less than the medium outside it. Now what happens in that case, if you were to go back and derive the lens equation from the start, you would find that you've got exactly the equation I've given you, except that term would go to that, right, in the general case. So you can see that glass in air just gives you that, right? Now the thing is, if I had this situation where actually N1 was greater than N2, right, then that, of course, is negative, okay? So what that is going to do is flip the sign of your focal length, right? What you don't want to do is flip the sign twice, right? Let's say you decided that you also decided the sign of the radii of curvature dependent on the behaviour in whatever medium you were, right? Now, both of that R1 and R2, if you did that incorrectly, if you were to do that, then actually your R1 and R2 would now both be negative, because in this situation, actually, this same lens would cause a deviation away from the axis. But then you've also put in another negative coming from this, and you don't want to do that. So that's why I specified you choose the signs of R1 and R2 by the behaviour in air, and then the sort of n minus or n2 over n1 factor gives you another minus sign, if it, you know, or gives you a minus sign if it should. So it's all taken care of in this. Right, now I'm looking at the time. I think I'm going to run out of time to say everything I want to say, so I'm going to have to, I think, come back and start from this stage again tomorrow. So I think that's enough for now. Okay, thank you very much.